Hi everyone, in this video we will continue with the design and analysis of the deep foundation that focus on the topic of the friction resistant capacity QS. So we will go through the notes and also the exercise how to determine or to estimate the QS. As we know that we have the ultimate load carrying capacity Qu ultimate, the equation in general is equivalent to Qp plus with the Qs. The Qp is the end bearing capacity, or also known as the point carrying capacity, plus with the frictional resistance or the skin resistance that derive from the soil pile interface. So for this video, we will look at the friction resistant QS. So this is the equation that we have the total P is the perimeter of the pile section in unit meter. And we have the delta L is the incremental pile length over which P and F are taken to be constant in unit meter. And we have the F here is the unit friction resistance at any depth. Z that we have the unit is kilonewton per meter square. So we go straight to the method that we can use to get the QS. So we have the alpha method here, the alpha method for estimating QS. So for example, we have for the clay soil. So from the general equations, the total P times with the delta L and times with the F. So the F is actually equivalent to alpha times with the undrained cohesion Cu here. What is the alpha? Alpha is the empirical adhesion factors that is a function of the undrained cohesions and the effective stress. So we can use this table to get the variations of alpha. So we have the ratio of undrained cohesion with the atmospheric pressure, which is the 100 kilonewton per meter square. And then by having this ratio, then you can get the alpha value here. Thus, if we substitute F with the alpha Cu, so we will have this equation, which the QS is equivalent to alpha Cu times with the perimeter and times with the delta L. So the perimeter of this pile sections, it depends on the shape or the size of the pile. If we have the circular cross sections, all right, so for example, for pipe pile, so the P will equivalent to pi D. But if you have the rectangular pile, so the P is 2 times with D1 plus D2. So if you have the size is like rectangular size, so this is D1, so this is D2. And you have the, if you have the square, all right, if you have the square, so you will have the 4 times with the D. All right, the perimeter is the total length for each length and width for the pile. Okay, and then the F is the unit friction resistance. All right, that we can get it from the alpha Cu. So let's take a look at one example. So as you can see here that we have 3 layers of the clay soil, okay, with the saturated clay soil, and then with different thickness, with different undrained cohesions. All right, so a driven pipe pile in clay as shown in this figure. So the pipe has outside diameter. Okay, by knowing this, the terms is diameter, so we know that the cross sections of this pile is in a circular cross section, and the wall thickness is 6.35 millimeter. So calculate the end bearing capacity QP by Mayohof methods, and then calculate the skin resistance QS by using the alpha method just now. And then you can estimate the allowable pile capacity. So in this exercise, we will combine to get the ultimate, all right, to get the allowable by calculating the QP and the QS. The QP, as mentioned in the previous video, that how we can get the QP using Mayohof's method for the clay soil. All right, so we will go through together. So it's just like a recap. So in question A that we need to determine the QP. Alright, so identify the equation that we need to be used. Remember, we have this equation for the clay that QP is equivalent to 9 Cu under cohesions times with the area of the pile tip. Okay, area at this pile tip. Alright. So since we have the circular cross section, so the area of the pipe pile is pi d square over 4. So we need to identify which Cu that we will refer, since we have 3 different layers and 2 different Cu values. So we can consider, since this is for the QP, so our considerations at the pile tip. So the tip of the pile is resting on a clay with the Cu is 100 kilonewton per meter square. Alright, so the pile tip is in the area of this Cu, which is 100 kilonewton per meter square. Then after that, we can get straight away the QP by using this equation. Alright. So we just substitute that we have 9. The Cu is 100 kilonewton per meter square, and the area. So knowing that the diameter is 0.426 meter. So to get this area, this is the equation. So the total QP here is 117 kilonewton. Alright, so we already determined the QP. That next we need to determine the QS, the resistance, the friction resistance capacity. Okay, so now we need to determine the QS. So by using alpha method, so this is the equation. Just now we have look at this equation. Alright, so we have alpha CUP times with the delta L. So we need to identify parameters required. So firstly, we can determine the alpha for each layer. You can see there is this summation here. Alright, so we need to identify for each layer. Alright, for example here. Okay. So this is the table that we are going to use to get the alpha. So it's more easier if you can develop a table. So with different column here that we have the different depths. And then we have the undrained cohesions. And we have this ratio because we want to refer this value in this table. In this table 1110 here, and then we can identify the alpha value. Alright, so first of all, that the first layer is from the ground surface 0 down to 5 meter. So the Cu given here is 30 kilonewton per meter square. Alright, so we need to get the ratio that Cu divided by atmospheric pressure. So that 30 divided by 100, you can get 0.3. So now you need to get the alpha 0.82. Alright, so how to get the 0.82? Check at the ratio 0.3 here, and the alpha given here is 0.82. So that's why here we have 0.82. Now to the next layer from 5 meters to the depth of 10 meter. How it's become 10? We have 5 meters at the top layer, and then we plus with the 5 meter in the next layer, so we have 10 meter in total. So the Cu given here is still 30 kilonewton per meter square, so the ratio is equivalent from the first row 0.3 and the alpha also 0.82. Now for the next layer, alright, after 10 meter down to 30 meter here actually. Why? So 10 here plus with the 20 meter, so it becomes 30. So the Cu here is 100. Alright, so the ratio of the Cu over PA here will become to 1. So look at this table. So for ratio equal to 1, so the alpha would be 0.48. So this is how we get the alpha value from this table. Okay, then next step, what are the parameters? The next parameters is the perimeter of the pile tip. Alright, so the pile tip here is in a circular cross sections. We have pi times d, that the diameter is 0.406 meters. So the P here is 1.28 meter. Okay, then we can determine the QS. So by using these equations, we have all the information. Alright, so you can see we have, it's actually the same table as previous step, but then I add column for delta L and also another column for QS here. Because we need to consider for each layer, so that's why we add another column here. Alright, so for the delta L is 5 meter. So we already have a 0.82 for the alpha. So we can get the QS for this layer. So the alpha is 0.82 times with CU here is 30 meter. And then the parameter just now is 1.28 meter. And the delta L here is 5 meter. So times with 5, so you will get 157.44. Now go to the next layer. The delta L is still 5 meter. You can see here that the thickness is 5 meter. So the delta L is 5 meter. Since you have the same value of alpha, so you will also can get the same value for the QS because the delta L also similar with the first layer. And then go to the next layer. So for 10 to 30 meter, the delta L is 20 meter. Alright, the alpha is 0.48. So now we need to calculate the QS with alpha 0.48 times with 100 CU. And then this is the P parameter and times with 20 is the delta L. So you will get 1228.8 kilonewton. So the total of the QS here, consider for all the layers here. So we have 1544 kilonewton. Alright, so now we complete to get the QS. So next, we need to determine Q allowable. So the general equations is Q ultimate equivalent to QP plus QS. We have the QP and QS just now. We total this one to get the Q ultimate 1661 kilonewton. And at the end, we can determine the Q allowable by using the Q ultimate divided by factor of safety. So which is equivalent to 3. So that the Q allowable is 554 kilonewton for this example. Okay, moving forward. So now this is the Mayohof method to estimate the QS for sand. So we have this equation again, but then we will come across with the different equations for the skin friction F here. Alright, in this case for the sand, it has been observed that the nature of variations of F in the field is approximately as shown here in figure. So you can see that the frictions between the pile and the soil here will increase. The unit skin friction will increase with depth more or less linear here. Okay, it looks like linear here to a depth of L prime. L prime is a critical length, and then it will remain constant after the L prime. So we need to determine what is the L prime here. So you can see here that the L prime is roughly equivalent to 50 D. D is the diameter of the pile here. Alright, and so if we want to determine the F, so we need to consider this situation. Alright, and then if you look at the F equation, that we have the K times with the stress knot prime times with the tangent delta prime here. So what is the K? K is actually the coefficients of lateral earth pressure at rest. Remember that we have the key knot when you are studying about the returning wall. Alright, the lateral earth pressure that we have the key knot. So the K here is actually from the at rest pressure. So it will be different for different types of pile. Alright, for the board pile or non-displacement pile, so you will use that the key knot is equivalent to 1 minus sine phi prime. For the low displacement driven pile, so this is the range for the K, and for the high displacement driven pile this is the equation. So what is the difference between the low and high displacement driven piles? For the low displacement piles, for example, we have the open-ended pile. For example, the H section pile. Alright. compare with the high displacement pile, for example, is like the square RC pile, alright, or the closed-ended pipe pile, that when we driven the pile into the soil, it will cause high displacement. Alright, compare with the low displacement, the open-ended file like the H section, so it will cause low displacement. And the bot pile is a type of the non-displacement because we need to excavate the hole at first, and then you will have the bot pile after that. Okay. So for the effective pressure here, all right, the sigma prime naught here is the vertical stress at the depth under consideration, all right, and the delta here is the soil pile friction angle. So it's usually between 0.5 friction angle to 0.8 friction angle. Okay, it's more easier if we look at with the example. So we have example number 2. Consider that we have a 15-meter long concrete pile. So this is the cross section. So you can see here, this is the square concrete pile. All right, fully embedded in sand. This is the concrete pile, cross section 0.45 times 0.45 is square, knowing that this is the high displacement driven piles. So the unit weight is 17 kilonewton per meter cube and the angle of friction is 35. Given the coefficient is 1.3 and the delta is equivalent to 0.8 angle of friction. So we need to identify first the end bearing capacity, QP. So you can refer to the previous video. And the estimate B, you need to estimate the frictional resistance QS, and at the end, estimate the allowable bearing capacity using the Fs equal to 3. Okay, so first kali, we need to determine the QP here. Alright, so what is the equation need to be used since it's fully embedded into the sand? So this is the equation. So C will equivalent to 0. So we will have this equation. So now we need to identify the bearing factor and subscript Q star here. Alright, knowing the angle of friction is 35 degree. So refer to this table, look at the angle of friction. So you will have the bearing capacity factor here is 143. Then after that, alright, so we will proceed to get the QP. Alright, by using this equation. Okay, NQ is 143. Alright, so here we have the area. Okay, since the cross sections is square, so 0.5 times 0.5. Unit weight here and the length of pile here. So 17 times with the length of pile of 15 times with the NQ star here. So this is the value of QP. But don't forget to compare or check with the limitation equation APQL here. Alright, and then you compare with the QP in this tab. Alright, so this is the equation again. You can refer to the previous video. Alright, how to get the Q limit here. Alright, don't forget to time with the area to get the unit of kilonewton of the load. Alright, okay, just substitute all the information. The angle of friction here is 35. So you will have 1014 kilonewton. So compare these two values, 7384 and 1014. So we will make sure that fulfill this requirement. Okay, is equal or less than 1014. Hence that the QP that will be used is 1014 kilonewton. And then we need to determine the QS. Alright, we need to determine the QS. The equation to be used is here. Alright, so we need to identify the F value here. So in the F equation, we have the sigma prime naught here. So it's actually derived from this equation, gamma unit weight times with the L prime here. So we need to identify first the L prime, which is equivalent to 15D. Alright, so you have 6.75 meter. Okay, you just substitute and then you can get 114.75 kilonewton per meter square. Now to get the F for this depth that Z from equal to 0 to L prime. So we have F equivalent to K sigma naught prime tangent delta prime. So it's actually based on this situation. Alright. As we increase the depth, the effective pressure will also increase linearly, more or less linearly, till they reach the L prime or the critical depth here. As we calculate here that the critical depth is 6.75 meter. So we have that this effective pressure is 114.75 at the critical depths. So once it reach at the critical depths, the effective pressure will keep constant towards the end of the pile length. So now we need to calculate for different sections of the effective pressure. So now for the depth that more to 0, but that is less or equal to 6.75. So we have this equation. All right. So this is the first section that we need to consider. Okay, with this depth limitation. So to get the F, this is the F. Then the K here, as mentioned in the question, is the coefficient. Given here is 1.3, coefficients of the lateral earth pressure K. So here 1.3 as mentioned in the question, that K is 1.3. And then we have the effective stress prime here. As we calculate just now. Alright, so at the critical depth, we have 114.75. But we need to consider this section first. Alright, so in order to get the effective pressure, we will consider an average value. Okay, we will consider an average value. So let's say to get an average, just divide by 2. Alright, the effective pressure here, divide by 2 to get an average of the effective pressure knot. Then here is the tangent delta. Alright, we have tangent delta is equivalent to 0.8 angle of friction. Okay, then we will get the F here is 39.66 kilonewton per meter square. So from this, we can calculate first to get the QS for this depth. But then don't forget to get the parameter since this is the square concrete pile. So we can simply get the parameter by 4 times with the 0.45 since it has a similar length for each direction. Okay, so this is the equation to get the QS. So this is the parameter. This is the L that we are considering at this step. And then this is the F. So we have the QS for this part is 481.87 kilonewton. So now we will continue with another length here that we should have another length for 8.25 meter. To make it total length is 15 meter. Alright. So for the depth that is more than 6.75 but then is equal to 15 meter. So we still have this F. Alright. So knowing that after each reach, the L prime here or critical depth here, critical length here, it will remain constant. It will remain constant. It will remain constant with 114.75 till the end of 15 meter length of the pile. So we can calculate the F. So we have the coefficient here. This is the coefficient of lateral earth pressure. So this is the effective pressure and we have the tangent delta which is 0.8 angle of friction. So you will have the F is 79.32. So the parameter is 1.8 meter and then at the end we can calculate for this section, we can calculate the QS for this section by using this P and the balance of the length is 15 minus 6.765 And the F friction here is 79.32. So you will get the QS is 117.90. And then at the end, you will need to calculate the total QS. Alright, the total QS is from the first section and also this section. So 481.87 plus with 177.90, so you will have 1660 kilonewton. So we complete the frictional resistance QS. So now we will continue with the allowable bearing capacity. To get the Q allowable, we must need to calculate the Q ultimate. We have the QP plus QS. Then the Q ultimate will equivalent to 2674. Then to get the Q allowable, by dividing the Q ultimate with the factor of safety, then you will get the Q allowable 891 kilonewton. And this is the final part. So the calculations of the QS, the estimating QS based on the SPTN value. So this is this equation. The difference again at the friction here, F average here. So P still the parameter, L is the length of the pile, F here is the screen friction. So it will become two different equations for high displacement and low displacement driven piles. Alright. So let's go to the example. Here mentioned the concrete pile, it is square. So understood that this is the high displacement piles. Alright, so we have the series of the N values. So we need to determine the frictional resistance QS. With the pile length is 15.2 meter long. Alright, so for this step, so which equation that we need to use, since this is the high displacement driven pile, so we will use this equation for the general equation based on SPT, but for the friction here is 0.02 PA times with the average N value. So PA is the atmospheric pressure, N60 here is the average N value for the top of N pile. Okay, now how to identify the N value? Right, so we know that the pile length is 15.2 meter. So we allocate where is the 15.2 meter. Now we need to get the N value that from the top, for the top of 15.2 meter. So we need to look at the above from the end of pile. So we have 10 value of N. So we need to average all these 10 values. So you will have 15 here. Then by having the N average, so you can use this equation to get the QS. So again, this is the square pile. Okay, we know that this is the square pile. The B is similar with the L size. So can get the parameter by 4 times D. And then you can get the friction average here. This is the 0.02. This is the P atmospheric pressure. And this is the N average. So you will get the friction is 13 kilonewton per meter square. Finally, to get the QS, we have the parameter and then times with the length of pile and times with the average friction. So finally, we will get the QS is 556.32 kilonewton. So this is how we use the SPTN value to get the resistance friction, to get the QS. That's all. Thank you.